So that's our introduction to intermolecular forces. These forces that exist between molecules. So why is it important? Well, it really describes why liquids, especially liquids, do what they do. If I put this paper towel in this beaker of water, what happens? It absorbs it, but if I just keep it at the same height, I should have put it in the beginning of class, and you would have seen it, because it takes a while. Water goes up. What's the word? It starts with C. Capillary rise or capillary action, right. This is how they think water actually goes up the trees, right, and goes to the leaves and things. And the reason why it's doing this is surface tension. And we're going to talk about what surface tension is. But that's why capillary rise, capillary action works. What they don't know to this day, it's weird how we can put guys on the moon and have things go crawl around on Mars and send the signal back, but we don't understand how water can go higher than 23 feet in a tree. Do all trees stop at 23 feet? No. But that's as high as surface tension will get water to go, is 23 feet. So we have more things to learn in our planet here, but so something complicated must be going on here. So let's jump into what surface tension actually is here. I've got a paper clip, a boat. We've heard of the word surface tension. I take a hunk of clay, drop it in water. Jose, it's going to what? Sink. Yeah, well, it's definitely sink. I take the same size clay, make a little boat out of it, right? Yeah, capillary action is really making that guy go up. And set it in there nice and gently, it'll float. Okay. So that guy's floating. Well, let's pick on some people here. It's floating, oh, Mia, because why? Why is it floating? Why do boats float? Is it surface tension? Density. It can't be surface tension because what? The surface is that, yeah, the boat went under the water. It broke the surface. So it can't be surface tension. Yeah, it's all about density. That's why boats float. This paper clip is floating not because of density, but because of surface tension. It hasn't broken the surface. Okay. So I think we need to get into the units of surface tension in order to figure out really what's going on here. Does anybody? Oh, it says the units. Right? Big J over meter squared. Ah. Come on. There's our units. We've seen big J before, Alyssa. What is it? Joules. It's a unit of, what does it describe? Anybody? Heat, energy, electrical energy. There's always different types of energy, but energy in general and heat. Yep. How about meters squared? Cameron. Meters squared. Now, meters was distance. I heard someone say distance. But this is meters squared. Area. So joules per meter squared is energy per unit area. So surface tension is what you're physically trying to do. You're physically trying to stretch a liquid, the surface. It takes energy. It takes energy to stretch the surface of a liquid. So you can actually measure this energy. They've got these instruments, and they figured these things out. And here's some plotted out, right, for different solvents. There's their surface tension. It takes energy to stretch things. And what's really going on here, once I think you see that, maybe this makes more sense. But they're trying to illustrate in this diagram that you've got some molecules that are in the bulk and some molecules that are up here on the surface. Okay. And which one do you think would be at a lower energy? The ones in the bulk. Yeah. It's kind of like, I can't get away from the idea that balls like to be at the bottom of a hill. Okay? And this has the most interaction. Everything's pulling into it. There's all these other molecules around it, all these intermolecular forces. And this is more stable than the guy up here. But this guy wants to be stable. So what he's going to do is he's going to get the maximum number of interactions possible. And that gives rise to this curved surface. But there's still these intermolecular interactions going on at the surface. Not in all directions, but it maximized it. And since those interactions are there, you can't just, there's something there that you got to pull apart in order to break the surface. So you got to, here's the energy. You could actually calculate it, how much energy it takes to break that surface, to stretch it a certain distance so you can get inside there. Okay. I don't know if you've heard, Jose, of these solvents, benzene, blood, glycerin, water. Do they all have the same surface tension? Enrique, what's going on? Why would different solvents have different surface tensions? Different? Okay, they have different masses. That's going to be that will be in one of the answers, yes. Well, in general, you can say they have different intermolecular forces. And just there being different sizes, Enrique is exactly right. That's one type of intermolecular force. Okay. So they have different intermolecular forces. And we're going to talk about the different types. Viscosity. Is anybody from up north? Nobody's from up north. What I got to do is I got to find this video. I saw this video of, it's really neat, because when you're up north, it's a big deal what type of blank you put in your car in the winter. Well, washer fluid, true, because it'll freeze and that wouldn't be good. But I'm thinking more about trying to start your car. Oil. What type of oil you put in there? Because what's the purpose of oil? Yeah, keep things nice and going nice and smooth. Lower the friction as much as possible. Okay, so all that oil's laying on the bottom of the oil pan, right? When you're going to start your car, you're going to turn the ignition, get things moving. Well, if that oil doesn't freeze, it just changes its viscosity with temperature. So you want something that, if it's really cold, would this oil be really viscous or very low viscosity? As things get colder, what happens? They get more viscous. What does that mean? Bowdy, what does that mean if something's more viscous? How would you picture that?
No idea.
Yeah, like more syrupy. I picture that too. Like they say that if you want a really good ketchup, remember that ketchup commercial? That if it's more syrupy and thicker, it's supposed to be better. More viscous, it's supposed to be better. So anyway, the oil story with your car. If you put in the wrong oil, that stuff is so viscous, it drops out of the bottom and doesn't even hardly move. So you want to put a very low viscosity oil in your car in the winter up north. Otherwise, as it gets colder, it's going to be so viscous, it's not even going to move. You can't even start your car. It just drops out of the, it's like a block in there. Okay. So most solutions, most liquids, you can, if I pull this stuff out here, make my little boat out of here, capillary reaction's going pretty good there. Well, I can just leave it in there. If I start stirring this, I don't know if you've ever played in the kitchen. You guys have stirred stuff. Typically, as you get going, I don't know if you can really tell, but does it get easier or harder? It's easier, right? And that's just how everything is. So, but not everything. Not everything. And there's this cool video. It's kind of long, but I think we have time to burn today, so we're going to take a look at it. Not everything. If you take cornstarch, mix it with the right amount of water, it behaves opposite. In other words, the harder you push on it, right, it doesn't become easier, it becomes a heck of a lot harder. I mean, swimming in water, oh yeah, sounds easy. If you want to swim in a solution of cornstarch, you have to barely push on the stuff, right? Because the harder you push, the more it's going to resist. That's called a non-Newtonian fluid. Let's see here. So these guys, they filled this solution with cornstarch, and it's in Argentina or some weird thing. It's all blurry, isn't it? Yeah. Is it warm in here? Is it hot? Is it hot in here or not?
I'm not hot. It's a little bit, though.
It's fine. What I don't get is, what if that guy swallowed some of this stuff, right? Imagine a liquid that you can't push. And the harder your throat try to push or get it out, the more it's going to lock up. There must be some setting on there I'm losing because it looks awfully weird. Okay. What are the names of the intermolecular forces? So you want to remember one of them? Kenneth, you remember one of them? What's that?
Mass.
Yeah, mass is one of them. And that's going to be the weakest one. Call it. I'm going to put it on the bottom. Van der Waals. Van der Waals. And they also call it, yeah, we should put all the names on there. Very good. Thank you for saying that. London. They also call it, starts with a D. No, that's going to be another one. Dispersion. So I guess we put these in parentheses. They're all the same thing. Dispersion. So these are forces that act between molecules that cause them to stick together. Okay. So these three types of forces are what creates liquids, what gives rise to surface tension, what gives rise, right, for all these different properties of liquids. So if you have just this type of intermolecular force happening, and remember this is the stuff of mass sticking to mass. It's the reason why, oh, you just moved into your dorm room, but it might be happening already. Look under your bed. You start seeing these little, what are they called, bunnies? Dust bunnies forming. Mass sticks to mass. You can't stop it. So that's an example of a dispersion force that you can actually see. But the point is how can you increase the strength of these dispersion forces? Even though they're really weak, how could you make these dust bunnies stick together even better? Pretty much all you do is just make things have this, whatever's causing these intermolecular forces, whatever the compound is, make it more massive, make it more flat, right? Because then it could stick together better. Okay, so typically what we're going to worry about, though, we'll just say just increase mass, size, area, something like that. That's the thought that I want you to have in your head. That's how you make dispersion forces stronger. And in fact, you know what gets kind of complicated is that mass sticks to mass. That means every single compound exhibits dispersion forces, or London, or Van der Waals, whatever you want to call it. Every single compound. There's the ones that are heavier and more massive, higher molecular weight, stronger Van der Waals forces. Oh, Andre, do you remember another one? Someone said it, or the D. Dipole, dipole. Dipole, dipole. Okay, now these forces are a little bit stronger. Well, actually, a lot stronger. What's a dipole? I think the only time you may have heard this word is at the end of last semester. We said, okay, we made this big table, and we said that these molecular shapes are sort of the P, polar. If something has a dipole, it means that they're polar molecules. Okay? So you make, if the molecules are more polar. So it's for polar molecules only. How do you spell molecules? Molecules. Now, how do you know, Steph, if you have a polar molecule in the first place? Yeah, positive end wants to stick to a negative end. But how does a molecule generate a positive end or a negative end? It was the E word. F is the worst, or the best. Electronegative. Electronegative meant it just wants, in this molecule, you're supposed to have, remember we have covalent compounds and ionic compounds. Ionic compounds were salts, right? A metal and a non-metal, right? You had cations and anions sticking together just because they're plus and minus. We're not talking about that. We're talking about molecules. So remember, to have molecules, you can't have a what present?
A charge?
Metal. You look at the chemical formula and there's no metal, you know it's a molecule. And what's holding that together are covalent bonds. This sharing, remember the sharing story? Okay, sharing electrons, that's what's held these things together. Nobody knows whose electrons are whose, but they're not Are they shared equally? Not shared equally? The E word tells you who's the, what do you call selfish, right? The E word, electronegative, is going to suck up all the electrons, well, most of the time. So the electrons will spend more time around fluorine than any other element in the world. So F is always partially negative. Okay. So the more polar it is, the stronger that dipole. And how do you make it more polar? A bigger electronegativity difference. Like if you have F and O bond versus F and TE, see, they're just separated more. Right? See how F is really close to oxygen. So that's not a whole lot of electronegativity difference. But F and TE, that's even more polar. Or HF, right? Something like that. One more type of, the strongest type of intermolecular force, it's called blank bonding. Hydrogen. H bonding. Hydrogen bonding. Okay. So we've got the strongest type of intermolecular force, hydrogen bonding. Okay. So how do you make, well, I guess H must be present in the molecule. In the molecule with what elements? They have to be really electronegative. There's only 3 of them. So in order for you to have hydrogen bonding is really, I don't know why they even do this actually, because hydrogen bonding is dipole-dipole bonding. They're both dipoles. But they're really, really strong dipoles. That's why they characterize them differently, I guess. So you have to have hydrogen present with the 3 most electronegative elements. Fluorine is one of them. Anybody guess another one? Oxygen. One more? Yeah, you'd think, but it's nitrogen. Nitrogen. Okay. Okay, so when you have hydrogen present with fluorine, oxygen, or nitrogen, strongest, and that kind of makes sense because it is in a world of its own. There's water, right? Definitely has hydrogen bonding, and it's way off. It's not off the chart, but it's as high as it's really high. So it makes sense, I guess, to make hydrogen bonding in a whole separate category than dipole-dipole. But it's still dipole-dipole. Okay. So we've got some oh, I didn't show you. Sorry, I forgot. I wanted to make this stuff because today, remember, I said we had time to burn, so. Here's cornstarch. And what I'm going to do is make some of that, what fluid, Megan? What's it called? Starts with an N. Anybody help her? Non-Newtonian. So I need to, you want to do this at home, you need to add some what to it? Water. Now this is where you can screw up. So you got to add the water slowly and have patience here. And then when it starts doing something really strange, you know you're done. So a little bit, that can't be enough. You can already stir it and you can feel something funky's going on. Because when you'll see, I'm going to pass this around, and when you want to stir it, you want it, right? It behaves the opposite of what you're used to. So it's really hard to stir because my brain can't calculate. Oh, if I want to stir this, go really slow. But that's not how you stir things, right? But that's good enough. I mean, it's not. I could mix it up better if I had more patience. But all I want you to do is just play around with this. I mean, if you want to put this through the non-Newtonian fluid, yeah, you think, oh, I'm just going to jam it through there. Jam it through there, it's like hitting a rock. But if you just kind of set it out or just let it fall on its own, there's like no resistance at all if you let it fall on its own. So just don't drink it. It'd be interesting to see what happens, but I don't think we should do that experiment. Okay. So we've got some different molecules here. All right, and let's see if we can identify the intermolecular force that's going on between them. We've got this first one, Bowdy, A. What type of intermolecular force would you say is going on there? Now they might just, I think the homework might look more like this. You've got HCl. They say, hey, this is a liquid. What's the intermolecular force that's going on? You have 1 out of 3 chances here. Van der Waals always works because it's stuff. So you can never go wrong saying van der Waals or dispersion or London or whatever. I don't forget what word the book uses the most. Right? But that's not the strongest. If that's the only one, then you're done. But there's a much stronger one that the book Kendall's probably going to expect you to say. Well, it's got H, but it doesn't have O, N, or F. Dipole, dipole. Because is this a polar molecule? That's really a hard question very often. In this case, it's easier to answer. H and Cl, yeah, chlorine's really electronegative. It's close to F, and it's just H. So, yeah, they're not going to share, and it's just going to be polar, and, yeah, dipole, dipole. But what if you had something like, let's add another one. Let's call this, I don't know, A prime. Carbon dioxide. Mia, what would you say? And like if you're going on a picnic, Mia, and you don't want to get all your little sandwiches wet and stuff, so you go buy some dry ice. What's dry ice?
Isn't it frozen CO2?
It's frozen CO2. So that means CO2 is a solid. There has to be some intermolecular forces going on there. What type of intermolecular force, Mia, exists with carbon dioxide? Remember, it's always safe to say one of them. Always safe to say van der Waals. So that's always one of your answers. But is that the only one? Now, do you see why this is a complicated question? There's no H, so it can't be H bonding. Now, there could be dipole-dipole unless this molecule is perfectly what? Perfectly linear. So you'd have to go through, do the Lewis dot structure, do that whole valence shell, electron pair, repulsion theory, Vesper, and see whether it's linear or not. You pretty much don't have, you don't have any choice. If they give you something like CO2, you have to go do the Lewis dot structure and see what its shape is and follow that table, whether things are polar or not. So CO2 is actually linear. So this is your only answer. Van der Waals. How about B? B is just H2O if you don't see it. Now you got H bonding. And don't forget to also add what to your answer? To add H bonding and, Enrique? Van der Waals, right? But the major one is going to be H bonding, right? Because it's the strongest.
Why do we add that one?
Because stuff sticks to stuff. That's why. Okay, now you've got a gecko on a window. What would you say for that, Kenneth? A gecko on a window. Van der Waals. I would agree with you. Van der Waals. Stuff sticks to stuff. However, well, let's write dispersion first, I guess. However, I read this recently, and I don't know why you guys are biology majors, just disgusting. I'm sorry. I mean, who's going to go analyze these little gecko feet and just do what they need to do to find out that it's not dispersion. It's actually, there's water on, little tiny water droplets on these guys' feet. So there's actually hydrogen bonding going on. That's why these animals can stick to windows. But anyway. How about number 1 here? The heat of vaporization. Megan, what the heck is the heat of vaporization? What is that? The heat it takes to vaporize something, yeah. And the heat necessary for something to go from what state to what state? Liquid to gas. So this is getting into that stuff that we talked about last class period, where if I've got this beaker of water, and I want to find out how much energy it takes to boil this stuff. So yeah, I'm going to need the heat of vaporization. So, right? And multiply that number by the amount of stuff I've got. When something is boiling, is it changing temperature? Right? My wife bugs the crud out of me on this. She's making macaroni and cheese. That burner is cranked up so high that it's glowing orange. Will that make the water any hotter? No. Right? Water can't get any hotter than its what point? Boiling point. Now, you could make the water boil hotter. She could do this. If she did what? What would she have to do what would she have to do differently? If she wanted this water to boil at a higher temperature? Change the pressure. A pressure cooker. Seal it up, essentially make a bomb, right? So the pressure's getting higher in there, and it's going to boil at a higher temperature. But you're just wasting energy. So anyway, things don't get hotter than their boiling point. So what I was getting at here is if you want to get this beaker to boil, there's 2 steps. First, you have to apply a bunch of heat just to get it to the boiling point. And then once you get it to that boiling point, whatever it is, according to the phase diagram, that temperature stays. It stays there until all that liquid is turned into a gas. Then it's a whole other state and temperature skyrockets. Okay, so Megan, you're right. Heat of vaporization is the energy it takes to convert a liquid to a gas. But you got to get it to that temperature first, that boiling point. So we've got chlorine, hydrogen, and nitrogen. There are these different numbers. And it looks like Andromeda, they've got 20.4 for chlorine. Liquid hydrogen is 0.9 and liquid nitrogen is 5.6. Are the numbers what you would expect? And the whole idea here is this intermolecular forces. Does it make sense that chlorine is 20.4 and hydrogen is 0.9, nitrogen is 5.6? No? The only thing that you can use to answer this is intermolecular forces. So what's going on there? Alyssa, what's the type of intermolecular force that's happening in every single case? Van der Waals. Is there any other type of force that's going on with those liquids? Any other type? No. Van der Waals is it. So how'd you make Van der Waals stronger? More mass. So is the most massive guy have the highest heat of vaporization? And the least massive the smallest? That's the answer. That's the answer. Hydrogen is the lightest, so it's the weakest Van der Waals. Chlorine's the heaviest, so it's got the strongest Van der Waals. So that's why it's got a higher heat of vaporization than hydrogen. They're all really weak, but it matches intermolecular forces ideas. So with that thinking, try answer number 2, then I'll ask somebody. Cameron, what do you think?
I'm just kind of confused. Like, I was looking for.
Yeah, keep going.
I was looking for a weight on that.
Yeah. So this one, weight works if the only type of intermolecular force is this van der Waals. But that's thrown out. Well, I guess that's not thrown out the window. You can use it for two of these guys because that's the only type of force that's occurring. Which two? The two on top, exactly. So you use the weight story to answer those two. But that's not going to be enough to say why this guy is so high. And what do you say? Anybody help him? Well, dipole is correct. But there's a better answer. Hydrogen bonding. Because you have O and you have H. And that's the strongest. It's the strongest type of intermolecular force. Even though it's lighter. I mean, oxygen has a higher molar mass than this stuff does. But that's okay. It's hydrogen bonding. It's the strongest. So that dominates. And that's why it's so high. Arrange the following substances in order of increasing magnitude of London forces. Yep.
Why does neon have a lower
Whoop.
O2 than
Neon is 1.8 oxygen. So neon has a molar mass of what? 20 is the molecular weight. But then oxygen is 32. So that's why. Try number 3. Increasing magnitude of London forces. So you would list which one on the bottom? Jose, you'd list which one on the bottom? Which had the weakest? The middle one. Then everybody, it would be right? Just going by molar mass is all. Right? Because you're getting bigger and bigger and bigger. What if, realize you got to be ready for this type of question though. What if in the homework, Enrique, I bet you is going to say this. They're going to say arrange, it's the exact same question, but arrange them in order of increasing boiling point. Would the list change? Right, now think about boiling. What makes something boil? That molecule has to actually leave. It has to pull away from all the other molecules and leave the solution. So boiling point is increasing the temperature, and then it converts from a liquid to a gas. So as you're increasing the temperature, well, these little molecules, they start doing what differently? Moving around faster. So you finally, they're moving, they have so much energy, they can leave. So the stronger the intermolecular force, the higher or lower the boiling point. It should be the higher. So nothing changes, right? They could also ask the question, arrange them in order of increasing what tension? Surface tension. Does anything change? No, because the intermolecular force is the strongest intermolecular force is going to give the strongest surface tension. It's going to give the highest boiling point. Okay, let's try number 4 here. Oh, thank you. Oh, now it's good. It's really nice and mixed up good now. It's disgusting. It's almost too much water, though. The halogens from a series of compounds with each other. Form. Must be form. Examples are bromine chloride, iodine bromide, blah, blah, blah. Which compound is expected to have the lowest boiling point? Which one had the lowest boiling point? Andre, I haven't picked on you at all. You didn't turn anything in?
I did.
How did I skip you all day?
No, you call on my phone.
Well, I'll call on you again. Which compound would have the lowest boiling point? What's the trick to do this?
One of the lowest magnitude London forces. So
Oh, not London forces, though. Because these guys are the P word. Polar. So that's why I think the homework is going to get you. You want to go by weight, but that works only if that's the only type of force going on. But these guys, they're different. That means they're gonna have some electronegativity to them. So the compound with the lowest boiling point would be the most polar or the least polar? Least polar.
I know when to go by weight and to go by volume.
Okay, I think what you got to do. Audrey's question is, how do you know when you're supposed to go by, like this guy, go by weight?
Yeah.
Here, I'm saying, oh no, you don't go by weight, you go by polar. Because what you have to do is you have to look at that compound and see look at the difference. If the molecule is polar, you have to go by polar. If the molecule has hydrogen and ON or F, you have to go by hydrogen bonding. If the molecule has neither of those, it means it's nonpolar. You have to go by van der Waals. Because van der Waals, while all these molecules are polar, van der Waals is still there, but it's really weak, so it's not going to tell the story. You can't stop it, but it's really weak, so it doesn't even matter. Weight doesn't fall in. So the one with the lowest boiling point means it has the weakest intermolecular forces, and you have to go by polarity. And the reason why I know you go by polarity is because these guys are definitely polar, because they're different. If I was going to go by van der Waals, I can't have CLF. It would have to be what? Cl. It has to be the exact same thing, so it's nonpolar. So I'd have to have Cl2, I2, Br2, right? F2, that sort of thing.
That's an I.
It should be ClF, chlorine. Okay, ClF. So which one would be the least polar? The two that are the closest together on the periodic table. ClF is really close. I mean, they all are. Look at that, BrCl's on top of one another. I should change this so it's more obvious.
Oh, yeah. It would be I.
IBR. Oh, they're all right on top of one another.
Yep.
Right? But IBR is probably the least polar, least electronegative in the first place, and they're right on top of one another. I'd probably say IBR too. That's what I would guess too. All right, so have a good day. Have a good weekend.